we can come to our next and last speaker of this section, Rouven Koch. He's a PhD student in the group of José Lado at the university in Aalto. And he's working on deep learning methods for condensed theory. So where he focuses on also on generative models such as adversarial neural networks. And I'm looking forward to hear about how adversarial neural networks can be used to design quantum matter. So,
hi, thanks for the nice
go
introduction.
ahead, please.
And thanks to the organizers. Is it okay? A bit up? Okay, it's been a while. Yeah, and thanks to the organizers for the chance to present our work about simulating quantum many-body matter with generative adversarial networks, or CGANs in this case. And one of the main applications of GANs is image generation. So I want to start this talk with a small quiz. So here you can see two cats. One I've taken from the website These Cats Do Not Exist, which uses this generative adversarial networks to generate fake images. And for the human eye, I think it's really hard to distinguish between real and fake images. In this case, okay, it's the right one. And we can play basically the same game also for physical quantities. In this case, I show you two spectra. I will explain shortly what exactly we'll see here, but for now it's just for the sake of demonstration. And the question again is which image is real. And I think it's, for the human eye again, pretty hard to distinguish between real and fake images. And yeah, in this case again, the one on the right is real. But let me explain or motivation for this project on an example. In this case, we take a many-body Hamiltonian, a one-dimensional spinless spin 1/2 Heisenberg model given by this Hamiltonian, and we're interested, let's say, in the conditional or in the parameter dependence of this Hamiltonian from first the local alternating near magnetic field as well as the uniform Zeeman field, and we also introduce some hidden parameters in this Hamiltonian. In this case, just magnetic fields in x and y direction. And the quantity we are interested in is the dynamical correlator, shown here, which basically allows us to calculate these real space, or for example, for the spin 1/2 system, like this real space spectra, where on the x-axis is the side of the lattice, and on the y-axis the frequency range, and basically we see here the spin-on excitations of this many-body Hamiltonian. And these dynamic correlators are basically exactly solvable with tensor network calculations. The question that arises now, or that we want to answer, is what if we're interested in the full parameter space of the Hamiltonian shown before? So the first and easiest answer is, okay, we can compute each parameter combination by hand, which is for the dynamical correlator really inefficient and numerically demanding for most many-body systems, and also neglects kind of the hidden parameters included in the Hamiltonian. So the approach we follow is the following. We use deep generative learning methods, in this case conditional GANs, to simulate these spectra. So we take the conditional parameters as input, feed them in our algorithm, and obtain also these spectra from the dynamic correlator. And for the training, the difference is that we can train the algorithm on a subset of parameter combinations, which means we don't have to compute each parameter by hand. And due to the intrinsic randomness of these algorithms, it can also incorporate the hidden parameters of the Hamiltonian. Just briefly to mention the background we're using for the calculations of the training and validation set. We use two methods. First, the kernel polynomial method, where we use the Chebyshev expansion in terms of these Chebyshev polynomials, which we basically use to calculate our dynamical correlator, which we then can write in terms of the Chebyshev polynomials and Chebyshev moments. For the states of the system, we used the tensor networks approach, which is shown on the right-hand side, which basically means that we can represent our quantum state as a collection of interconnected tensors by contraction, as shown here, and especially for the one-dimensional case, which we're considering for this work, we're using the so-called matrix product states, but I won't go too much into detail into those methods here. Yeah, and briefly to show the architecture of the generative adversarial network, we have already heard about it before today, but let me explain it again briefly. So basically, the generative adversarial networks consist of two networks: the generator, which takes noise from latent space, and in this case, conditional parameters as input, and generates our spectra, and the discriminator, which distinguishes between real spectra and these fake or generated images from the generator. And during the training process, where this value function gets optimized, it's like a min-max game between two players. So first, the generator has to become really good in generating these realistic spectra, let's say, because the discriminator at the same time becomes really good in distinguishing between real and fake images, or fake spectra in this case. For the training and evaluation, so we consider basically three systems. The spin-1/2 model I've already shown. We also consider the spin-1 model and the Hubbard model. And we divide what you see here is on the x and y axis always the, let's say, parameter space for the conditional parameters. And for the training validation, we just cut out some parts of the parameter space in order to validate our system later. And to evaluate the accuracy of two images or of the two spectra, we use on the one hand the so-called structural similarity index, which is defined between 0 and 1, where it has only the value 1 if both images are exactly the same. So the closer it gets to 1, the better it is. And another measure is, for example, the energy bands, the energy offset, and the magnitude of the different energy bands shown in the spectra. The first part of the results, we focus on the generator, where we use the GAN as many-body simulator. And just to briefly mention the systems again, which we study here, I won't go into too much detail on the Hamiltonians. First, the spin-1/2 model shown before, which is basically a gapless many-body Hamiltonian featuring spin-on excitations. The second model we study is the spin-1 model, which is an interacting spin-1 system with topological order. And the last system we study is the Hubbard model, which is an interacting fermionic system. And the only things they have in common that we choose like conditional parameters, in this case 2 for each system, and also include some intrinsic randomness in each Hamiltonian. Coming now to the results or examples for results for the predictions or simulations with our algorithm for each of the many-body system for the Hubbard, spin-1, and spin-1/2. And on the left-hand side, we can see our generated images for one parameter combination in this case, and on the right-hand side, the exact calculations with our tensor networks or many-body methods. And as we can see already from the SSIM index, which is really close to 1, is that our generated images or generated spectra are really close to the exact calculations, which is also seen, for example, from the human eye, from the energy spectra and offsets of energy bands and other pronounced features. So what I've shown before is just one specific example. Now I will focus a bit on the whole parameter space for each of the models. So on the left-hand side, we trained our GAN on the full parameter space without cutting out a piece of training validation split, which is marked with these orange squares in this case. And on the right-hand side, we had this train validation split and tried to infer, let's say, the area inside these squares, which we cut out. And we can see that we overall see the same accuracy or same SSIM index, so same similarity even in the regimes which the GAN hasn't been trained on or has never seen before. So it learns kind of to infer or interpolate to these areas of the parameter space. And these fluctuations we can see here are due to the basically homogeneous fluctuations of the intrinsic randomness of the GAN, and also in the Hamiltonian, where we included the random parameters. The second part, we neglect, let's say, the generator in this case and only focus on the discriminator and use our GAN as, let's say, many-body assessor. And again, I want to ask a question to introduce this part. So just by looking at this image, could we guess what's the underlying Hamiltonian, especially considering the conditional parameters of the Hamiltonian, so the delta J and J2? And I think for the human eye, again, it's pretty hard to estimate the underlying Hamiltonian just by looking at the spectrum. So we, again, ask our CGAN, and what we see on the right-hand side is, let's say, the probability shown in the colors here from 0 or from low to high in red, where the spectrum is in the parameter space. And the exact location is marked by the X here. And our CGAN allows us to give us this confidence interval inside, let's say, this intrinsic randomness and fluctuations. And we also studied it for the 3 other systems. I won't go too much into detail for those due to some limited time. But as we see for the Hubbard model as well as for the spin 1/2 model, the GAN also allows us to, let's say, gain a confidence interval to in which area of the parameter space of the Hamiltonian the given image or spectrum lays. And to finish this talk, I want to give you a take-home message, which is that generative learning models can be a powerful tool for first the simulation, as well as the analysis of many-body systems. And if you're interested in some more details, it's already an archive, and I'll also be around here for questions. Thanks for your attention.
Thank you very much for this great talk. Do we have any questions yet? If not, while you think of your questions, let me maybe start with mine. So I have quite some. One question would be: so you train on a range of parameters, right?
Right.
And then you say you can cut some parts out, and then you can also recover the right results in those parts that are cut out.
Exactly. Yeah.
So how dense does this have to be? Can you, for example, train on an exactly solvable part and then extrapolate to other parts of the phase diagram?
So far, we just considered only exactly solvable to have like a benchmark in this case. That's also why we limited ourselves to 1D to get exact results with the tensor network calculations. But yeah, as we've seen here, it's the GAN as at least to infer the parameter space, which it has not seen before. So I'm not sure how it is for a complete different regime of the parameter space. I guess it has to have some training or intuition of that area. But yeah, in general, I think with the right training data, it would be possible to extrapolate a bit.
And just some small follow-up. Do you know what happens if you have a phase transition within the space of parameters you train?
We're already thinking about it.
Yeah.
In this case, the parameter space where we didn't have one. But for example, if we would look at the discriminator plots again, we would expect maybe a cut somewhere where the accuracy or the, let's say, probability goes immediately to 0 because the spectra are so different from the known area, let's say.
Yeah. All right, thanks a lot. Any further questions? Yes.
Hi, thanks for the talk. I was wondering how many data do you need for the training, and what was the size of the system you were simulating with the tensor network?
Okay, good questions. First, for the training data. For the exact calculations, I think we used around 2,000, but used data enhancement methods to go up to 30,000, I would say. But yeah, I think usually GANs are trained on a huge amount of data, and it would also, for this proof of principle, we try to minimize the amount of data required to get some at least accurate results. So yeah, that's for the first question. And the second one, we considered systems of size 18. And especially for the Hubbard model, if we want to calculate one of these spectra on your laptop, it would already take like 24 hours. So that's also one reason to achieve the speed up, because afterwards, once the GAN is trained and we want to calculate one parameter combination, it doesn't take 24 hours, it takes 1 second or less than 1 second. So, yeah, thanks.
Maybe a question regarding these strategies for data augmentation. So did you apply certain transformations of the Hamiltonian for that, or what was the transformations that you took into account?
Yes, we also
Like
added some, like, let's say, noise to the images
okay.
or to the spectra to change the intensity, and which basically changed the hidden parameters but not the conditional parameters. So we added some fluctuations which physically shouldn't affect the conditional parameter we choose to enhance the data.
I think we maybe have time for one quick question, but then we should go to the break.
Thank you. So my question originally was how many data points you needed, and you said 2,000. So what would be your strategy for problems that are hard to calculate? You think you could do some transfer learning from easier systems and then just calculate a few points for hardly solvable models?
That's one idea, for example, to use some single particle data which has like a similar shape, even though it's physically different, and then to just train a bit with a few from the many-body calculations, but we didn't do some tests on that. But it's definitely one topic we were thinking about to make it applicable for even larger systems where it's not feasible to calculate 2,000 samples. Thanks.
Okay, so let's thank Rouven again.